Hi and Assalamualaikum. Today we want to present on linear algebra with topic hardwood concentration in pulp and tensile strength of graph paper. Introduction. This project analyzed the relationship between hardwood fiber concentration on the tensile strength of graph paper using a least square quadratic fit model. The strength of graph paper is influenced by the composition of fiber used in pulp production, and change in hardwood concentration may result in nonlinear effect on tensile strength. The dataset consists of 10 observations obtained from the textbook with title Introduction to Linear Regression Analysis, where hardwood concentration is treated as the independent variable and tensile strength as the dependent variable. Quadratic model is applied to determine the best fitting curve for the data using both manual calculation and Mapper software. In addition, the error vector and magnitude of error are constructed to evaluate the accuracy and reliability of the model in representing the observed data.
Next is the Maple output. After we insert the data into Maple, we need to transfer the system to the matrix of AX equals to B, and we can see the output below. After that, we need to check the consistency of the matrix by using row echelon form. Since the augmented matrix is inconsistent, we need to proceed to find least square quadratic fit by using normal system in which A transpose AX equals to A transpose B. And this is the output of A transpose A and A transpose B. And after that, we need to use row echelon form REF to get the value of X. So the equation for the best fit quadratic is Y equals to negative 6.2265 plus 11.8362x minus 0.6398x squared. The output for the graph shown that the data is base fitted by a quadratic model because tensile strength increases to a maximum value and then decreases as hardwood concentration increases. The last one, we need to find the error vector. The error vector is calculated by using formula E equals to Y minus M times V, and we will get the answer for the error vector. And for the magnitude error vector is calculated by using formula of square root of summation of square error for every data. And this is the output below.
Step 1. Transform the system into matrix form. So we start by organizing our data into a matrix equation for A vector X equals to vector B. The matrix A, which is the contains the coefficient, and the vector X represent the unknown coefficient of the quadratic model. So the vector B contains the observed data values. This representation allows to apply linear algebra techniques to find the best fit quadratic curve. Step 2. Row echelon form using elimination row operations. Next, we check the consistency of the system by applying elimination row operations, which is ERO, to form row echelon form, which is REF. First, eliminate entries below the first pivot by subtracting the first row from each subsequent row. Then use the second pivot to eliminate entries below it in the second column. Finally, normalize the third pivot and eliminate entries below it. This confirms the system is inconsistent and ready for solving. Third step, least squares quadratic fit using normal system. To find the best quadratic curve, we use the least squares method and form the normal equations, which is A transpose A vector X equals to A transpose vector. After solve all the calculation, the quadratic equation we got is Y equals to negative 184989 over 29710 plus 12237578 over 10339080 x minus 66155593 over 10339080, which is x squared. This is the least squares quadratic fit for the data. Step 4. Compute error vector. Now we calculate the error vector. which is E equals to vector B minus A vector X. Subtract the predicted values from the observed values. These residuals show how far each point is from the fitted curve. Step 5. Magnitude of least squares error. Finally, we compute the magnitude of the error vector, which is square root of E. Then the result is equals to 13.4980. This is the total least squares error. A smaller value indicates a better fit, and here is the error is reasonably small, confirming that our quadratic model fits the data well.
Conclusion. In conclusion, a quadratic least square model was successfully applied to analyze the relationship between hardwood concentration in pulp and the tensile strength of graph paper. The quadratic model obtained through manual calculation was consistent with the result produced using Maple, indicating the correctness of the modeling process. The fitted curve closely followed the pattern of the data, with only minor deviation observed, which may be due to experimental or process variation. The small magnitude of least squares error further confirmed that the quadratic model provides a reliable and accurate representation of the relationship between the variables. Overall, this study demonstrates that the least square quadratic fit model is an effective method for modeling nonlinear relationships in real-world data.